we are starting in a new chapter, chapter 2, which is reasoning and proofs. So right now I just passed out the note packet for 2.1. Students are doing the warm-up of writing down something that you learned in chapter 1. I'll give you 30 more seconds. Just one thing. Maybe your favorite thing that we did. Okay. So this first lesson in chapter 2 is called inductive reasoning and conjecture. And this is something you do literally like every single day. You just don't know that this is what it's called. It's like using inductive reasoning and forming conjectures. Okay? You've probably looked at some like data to find patterns and make predictions, and that's pretty much all it is. Some of this is very like mathy with patterns. Some of it's not. Some of it's like real life stuff. So if you've ever been wondering, like when am I ever going to need to know this in real life? Today's the day. This is real life stuff. And just a couple of vocab. Okay. So inductive reasoning, the definition, it's making a conclusion based upon an observed pattern. So you're basically observing or looking at what has happened to figure out what's going to happen or to make a prediction of what's going to happen by looking at some like observations or facts or patterns. Okay? A conjecture is your educated guess of what's going to happen based on these observations and facts. So it's kind of like, if you've ever talked about hypothesis in science, like an educated guess, similar to that. So let me just give you like a quick example. So yesterday was Sunday. Today is Monday, Tyson's birthday. And those are facts, right? That's happened. Yesterday was Sunday, today's Monday. So looking at this pattern, I'm going to make the prediction that tomorrow is going to be Tuesday. That's using inductive reasoning. Looking at what's happened, yesterday was Sunday, today is Monday. My conjecture is that tomorrow is going to be Tuesday, based on what we observed and patterns, okay? Like I said, you use this every day. Here's another example. 20 cans from a factory were examined, and all 20 had been damaged. Okay, so that's facts, that's what's happened. 20 cans from a factory, all of them were damaged. So my conjecture or my hypothesis of what's going to happen next, my prediction, is that all the cans, all the future cans from the factory will also be damaged. Now, we don't know if this is true or not. That's why it's a conjecture. It's just an educated guess based upon the facts. Okay, let's look at a more mathy example. Here I have a sequence of numbers. 3, 6, 9, 12. So I'm looking for a pattern here. What are some ways? Let's just look at the first two terms. What are some ways I could get from 3 to 6? Add how many?
3.
Add 3 or times by 2, right? Those are both kind of like ways. Okay, so let's look at the next one. How do I get from 6 to 9? Add 3. How do I get from 9 to 12? So it's kind of looking like my pattern here is that I'm adding 3 to each term to get to the next term. So my conjecture of how I'm going to get to the next is add 3. That's your educated guess of what we're going to do next. Now we could actually go ahead and do this and make an educated guess that the next term will be 12 12 plus 3, which is 15. But that right there, folks, that's my estimation of my prediction of what's going to happen next when I add 3 to get to the next term. All right, let's look at one more simple example, then we'll step it up a notch. So I have these arrows. First one's facing up. Second one's facing to the right. Third one's facing down. What pattern do we notice here, Alex?
They like just turn clockwise.
Exactly, yeah. Turn clockwise. I like that. Rotate 90 degrees. Turn clockwise. That's a good one. Let's combine ours. So there's our conjecture of what we're going to do next. And if we wanted to predict the next term, we rotate it 90 degrees again clockwise, I think it's probably going to be this. But we don't know for sure. Could be something else really random. That's just our guess. Our conjecture. Okay. Try a couple more. They're a little bit more challenging. Write a conjecture that describes a pattern 2, 4, 12, 48, 240. Then use your conjecture to find the next item in the sequence. Okay, so again, I kind of start by thinking of some ways that I could get from 2 to 4, and we could add 2, we could times 2. But I look at my next and I'm like, ooh, 4 to 12. How do I get from 4 to 12? Times 3. Okay, what about 12 to 48? Times 4. Start to recognize this pattern. So it doesn't have to be like the same number every time. So here I'm timesing by 2. Then I'm timesing by 3. Then I'm timesing by 4. We could try this. If I take 48 times 5, do I get 240? Yes, I do. So my conjecture is that I'm going to times 6 to the term. That's what I'm going to do next based upon this pattern. So you could just say the next term will be 240 times 6. And then they do want us to use this to find the next term, and 240 times 6 is 1,440. So what I wrote in red, that's my conjecture, is that I'm going to times 6 to the next term, and it actually found the next term. Okay, any questions so far? All right, I'm going to let you guys try this one. It's a little bit harder. Write a conjecture that describes a pattern in the sequence 1, 1/4, 1/9, 1/16, 1/25. And see if you can figure out the next term. One more minute. Good job, that's right. Okay. Anybody notice a pattern?
It's a minus.
Okay, that's right. Ben?
So the first one would be plus 3, then plus 5, then plus 7, then plus 9.
On just the denominators, right?
Yeah.
So the numerators are always 1. That's kind of a part of the pattern. So he said denominators, add 3, add 5, add 7, add 9. So you're thinking that we'd add what?
11.
11 to get?
1 by 7.
Okay, that pattern works, and this is actually the next term. Well, according to the pattern. Okay, that was the same one Cole found. So you could say you're adding 2 more to the previous term every time, or you're adding an odd number each time, but it's going up, however you want to state that. I noticed a different pattern. But you could write that into words. What do we notice about our denominators? What kind of numbers are these?
Squares.
Perfect squares. Right here. So this is what I noticed. And again, you don't have, there's obviously more than one. You don't have to write this down if you don't want to. But here I have 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. So my conjecture was, hey, the next term is going to be 1 over 6 squared, which is 36. Here's my conjecture. Find the next term. Okay, you can also notice that the pattern that Cole invented, we started with adding 3 and then added 2 more each time. Then we added 5, then we added 7, then we added 9. So my conjecture is that we're going to add 11 to the denominator to get to the next term. Aren't these fun?
Yeah.
Okay, try this one. Write a conjecture that describes a pattern in the sequence. Then use your conjecture to find the next item, or like what the next figure would be in a sequence. Okay, take a look at them circles. For some patterns. All right, who thinks they have a good, educated conjecture? Alejandro,
I think the next term will be 15.
15 circles?
Yes,
Me too. Why do you think that?
because pattern goes +2, +3, +4, and most likely +5.
Good, you said that perfectly. Hopefully the mic picked up what you said there. Okay, so looking at this pattern, he said, we think the next figure or the next item, we will add 5. So 10 plus 5, which then to find that next item, you'd say 15 circles. If you wanted to draw a picture, oh, I didn't draw. You could. All right. There's some example of writing your own conjectures. Now, here's our other kind of new vocab term for this lesson. To show that a conjecture is true, you have to show that it's always going to be true. Okay? To show that a conjecture is false, all you need to do is give me one, what we call counterexample. It's basically one instance where that conjecture doesn't hold true. Okay? So counterexample, an example that shows the conjecture is false. So let me just give you like a real life example for a second. And then we'll do some with numbers. I was driving to work today, and my car suddenly stopped by Quick Trip. So probably my first thought, if I'm driving my car and it stops, is that I ran out of gas. Right? That might be my first, because I'm also really bad. I like to run on E. I like to play that dangerous game. You guys don't know. You're not drivers yet, most of you. I like to ride out the E as long as I can. So one possible conjecture, one possible guess based upon what happened is that I ran out of gas. Good thing I stopped right by Quick Trip, right? All right, so that's just my first kind of guess is that I ran out of gas. And then I look at my gas tank and I'm like, oh my gosh, maybe my mom filled up my tank for me. We actually have a full tank of gas. So that could be considered a counterexample because it proves this possible conjecture that we ran out of gas, it proves it wrong. Okay, and obviously there's other possible conjectures, but that's just an example of like what a counterexample is. So we're just gonna kind of do like a bunch of examples, and that's about it. It's kind of like the new stuff for today. So we have like 8 examples together. All right, make a conjecture about each value or geometric relationship. List or draw some examples that support your conjecture. Okay, so they want us to make a conjecture about the sum of an odd number and an even number. So I was just going to start by making some examples and just seeing any patterns. So I picked an odd number. I'm just going to use the one I used in my notes. I picked 17. Ooh, what does sum mean? Add, yep. And then I picked an even number. I picked 12. Added those together. I got 29. All right, somebody give me an odd number. 3. Somebody give me an even number. 26. Oh, those also add to 29. Maybe my conjecture is that anytime I add an odd number and an even number, I always get 29. No, that wouldn't make sense, right? Okay, let's do another one. How about 5 and 10? Okay, but what do we notice about all of these numbers, 29 and 15? They're odd. Sorry. Be so patiently. Raise your hand. So a possible conjecture, a possible guess is that the sum of an odd number and an even number will always be odd. Now, it's not possible for me to sit here and list out every single combination of adding an odd number to an even number, right? To show that this is true. But to show that it's false, can anyone think of a counterexample? Can anyone think of an odd number plus an even number where I wouldn't get an odd number? You're all right. There isn't one. This is true. Good job. This is so smart. This is true. All right, let's try another one. For points L, M, and N, LM is 20, MN is 6, and LN is 14. Ooh, this will throw back to some stuff we learned in chapter 1. Okay, well, LM is 20, and that's my longest segment, so let's draw this. LM is 20. MN is 6. Oops. LN is 14. Okay, so that picture would correctly represent that information there. Some possible conjectures I can make based upon this is that point M point N is in between points L and M. That could be one educated guess based on what information you're given. We could say points L, N, and M could be collinear. These are just a bunch of examples. You don't have to write them all down, but segment length LN plus NM equals LM. That could be another conjecture. All right, we'll take a look at some counterexamples next. So this time they're giving us the conjecture. We don't have to come up with it ourselves. They say determine whether this conjecture is true or false. Oops, I should say or false, not of false. True or false. If false, give a counterexample. If true, explain why it's true. All right, here's the first conjecture. If you have 3 points, A, B, and C, then A, B, and C are non-collinear. Is that always going to be true? No. We could have 3 points that are collinear. False. Counterexample. Go ahead and draw 3 points that are collinear. That would work. It has to always be true. Next one. If angle 1 is complementary to angle 2, then angle 1 is congruent to angle 2. What do you think? True or false?
True.
Who thinks true? I can't hear. Ben says true. You think true? What does complementary mean? Add to 90. It's false, yep. They could be. What would both the angles have to be if they were congruent and added to 90? 45. So they could be. But are they always going to be 45, 45 in order to be complementary? No. This is false. Counterexample. Maybe you have angle 1 is 10 degrees and angle 2 is 80. Those are complementary. Those would add to 90, but obviously not congruent. You could draw a picture if you wanted to. And angle 1 is only 10 degrees and you only need one counterexample to prove a conjecture false. Okay. The next ones are just a little different. They're telling us, hey, these conjectures are false. So find a counterexample that proves that it's false. The sum of 2 numbers is always more than the greater number. All right, so they're already telling us this is false. Can somebody think of a counterexample of when I add 2 numbers and the sum of it is not greater than the biggest number? Lillian, I saw your hand first.
-3 plus 5.
Ooh, -3 plus 5. You get 2. Is 2 greater than the biggest number here, 5? No, it's not. Good one. Another one?
10 plus 0.
Good one. I don't know why I put 10 in parentheses. 10 plus 0 is 10. Is 10 greater than 10? No, it's equal to. Okay, we only needed 1, but I like those examples. Nice one, Walker. I didn't think of that one. Next one. The value of squaring a number, I don't know what the number is, so we're calling it x, is always greater than the number itself. The value of squaring a number is always greater than the number itself. Counterexample. 1. Great one. 1 squared is 1. 1 is not greater than 1.
0 squared.
0 squared? Okay, good. Let's get a little more creative.
That is creative.
You're not wrong, Walker. That would totally work. Tyson, can you go on?
1/2 squared.
Oh, love it. 1/2 squared. Square the top, 1 square the bottom. Is 1/4. Is 1/2 greater than a 4th? Oh, sorry. I meant it the other way. Is 1/4? Is that value greater than the number itself? Is 1/4 greater than a half? No. Good. 0 would also work. All right. Last couple. We're almost done. Make and test a conjecture about the sign of the product of any three negative numbers. All right, so I just like to start with an example first. I'm just going to pick three negative numbers, and I'm going to keep it pretty simple here. 0 is not positive or negative, so you can't use 0. Well, let's say I have like -3 times -5 times -1. All right, I'm going to multiply three numbers. My brain works left to right. I'd probably do these two first and get positive 15. And then times it by -1, I'm going to get negative 15. Okay. We could try it again. Pick three more numbers. -2 times -2 times -2. Here we get positive 4 times -2, we get -8. So what is the product? What is the sign of the product in both of these cases? You can shout out. They're negative, right? Now let's think about that in any situation. Oops. If you have a negative times a negative, what is that always going to come out to? Positive product. And then what's a positive times a negative always going to come out to? Negative. So our conjecture is that the sign of the product of any three negative numbers, exactly like Alex said, is always going to be negative. It did say make and test this conjecture, so this over here, folks, this could count as testing it. Okay. With me? You're slacking. All right, I'm gonna let you guys do the last one. Make and test a conjecture about the product of any two even numbers. So let's start on a couple examples. Let's have two even numbers. Maybe what their products have that you see this pattern. Here were some of my examples. 2 times 2. Then I did 4 times 8. I saw someone do 4 times 10. Okay, what do we notice about all of these products? Okay. What else? They're all even. Is that what you're gonna say, Lillian?
Yeah.
Nice. Okay. The product of any two even numbers is always even, and this makes sense because they all contain factors of 2. So their product will also contain a factor of 2. Here's my conjecture. Here's my tests. That's the whole lesson.
Too easy.
Okay, that's a wrap on the notes. So the homework assignment that goes along with this lesson is the 2-1 worksheet, the 2-1 book assignment. Stop the recording really quick.
Yes.